This is the proposal for the Collaboration for Innovative Research on Aircraft Structures, otherwise known as CRAS. This is presented by Francis Webby, and this is for the client, the Air Force Research Lab. The contents of this presentation are as follows. There is the overview, the problem and the need, the plan, supplies and equipment, personnel, and deliverables. The proposal overview. This proposal, titled Collaboration for Innovative Research on Aircraft Structures, focuses on developing a simulation and data processing tool that creates accurate, time-resolved loading spectra for aircraft structures. By combining flight data, mission logs, and environmental inputs, the tool will generate tailored loading profiles that include maneuver-induced stresses, aeroelastic responses, and exposure to environmental effects. These spectra will be validated through comparison with the historical data and experimental results. The project is designed to meet a critical capability gap identified by the Air Force Research Laboratory, enabling faster, more precise structural assessments with reduced reliance on costly physical fatigue testing. Ultimately, this will benefit both the Department of Defense and the aerospace contractors by supporting more efficient aircraft development and enhanced structural reliability. The reason for this proposal is to obtain funding that will support the development of this tool capable of generating realistic mission-specific loads and environmental spectra for aircraft structural design. The core objective is to improve how structural loads are represented during the early stages of aircraft development by integrating real-world flight data, mission histories, and environmental exposures into a comprehensive simulation environment. There is a growing need within the Department of Defense, and particularly the Air Force Research Lab, to enhance the accuracy of structural predictions without the heavy reliance on expensive and time-consuming physical testing. Current tools often treat loading in isolation, failing to account for the dynamic interplay between mechanical stressors and environmental conditions, such as temperature, humidity, and chemical exposure. By addressing this need, our proposed tool will allow engineers to better predict fatigue, life, identify potential failure zones earlier in the design process, and support visual certification pathways. This aligned directly with the AFRL's goal of advancing aerospace systems integrity through innovation and simulation-based design methodologies. Once this proposal is accepted and funded, the project will begin with a formal kickoff phase. During this period, we will establish clear roles within the team, refine our technical plan in collaboration with the AFRL, and prepare all required infrastructure for simulation and data processing. The first major technical task will involve acquiring and processing the necessary data. This includes mission-specific flight logs, environmental data from relevant databases, and validated material behavior information. Access to this data may require special permits or coordination with existing military data holders. Following that, the core development work begins. Our team will begin to build the spectrum generation tool by integrating physics-based simulations, reduced order modeling, and machine learning techniques. This tool will align mechanical and environmental loads in a time-resolved manner to accurately represent real operational conditions. The validation is a critical part of this process. We will compare the generated spectra against historical load cases and real-world fatigue test data to confirm accuracy and fidelity. At the end of this project, we will deliver a complete package to the Air Force Research Laboratory, including the load spectrum generator, technical documentation, case tests, and integration guides. We will also remain available for a final 1-month support period to resolve any issues and ensure the client can confidently adopt the tool into their engineering workflow. This project offers several key benefits that directly support the needs of the Air Force Research Laboratory and the broader defense aerospace community. First and foremost, it enables more accurate prediction of fatigue and long-term structural durability by providing realistic mission-specific load spectra. These spectra reflect the actual conditions the aircraft face rather than relying on conservative estimates or generic profiles. By providing the quality and relevance of structural simulations, the project also reduces the need for extensive physical testing. This saves significant time and cost, especially during the early development and certification processes, where testing can be both expensive and a schedule bottleneck. Another major advantage is the acceleration of structural certifications. With validated load histories available early in the design process, engineers can make more informed decisions and reduce the likelihood of late-stage redesigns. This supports faster development timelines and greater confidence in airframe reliability. Additionally, the ability to generate planform-specific load spectra allows for better optimization of the aircraft for their intended missions. This helps both in military applications and in collaborative industry use, where missions performance and efficiency are critical. Finally, the project's deliverables will continue to provide value well beyond the initial development window. The load spectrum tool will be applicable for future aircraft programs, and the data it generates will support materials qualification, damage tolerance analysis, and regulatory certification for years to come, potentially over the entire life cycle of multiple aircraft planforms. This project operates by taking real-world data from several sources, including onboard flight sensors, historical mission logs, and environmental databases, such as those provided by NASA and NOAA. The first step involves filtering and normalizing these data inputs to ensure they are compatible and reliable. Once the data is prepared, modeled loads are added in, such as maneuver stresses, aeroelastic effects, and environmental stressors like temperature and chemical exposure. These inputs are then run through structural simulation tools such as FEA, Nastran, and fatigue analysis software to simulate response. The result is a time-resolved, validated load spectrum that accurately reflects how a specific aircraft planform is expected to perform over time in its actual mission-specific environment. The tool will be built with compatibility in mind, allowing it to integrate smoothly into the design and analysis workflows already in use by engineering teams. This tool will primarily be used within aerospace research laboratories and design environments where structural analysis is conducted. That includes both government research facilities like those operated by the AFRL and industry partners. During the early stages of the airframe development, engineers will use the tool to evaluate structural behavior under expected mission conditions. It will also support regulatory and certification bodies by providing a scientifically validated basis for estimating fatigue. Over the long term, this capability will find use across multiple aircraft planforms, especially those expected to remain in service for decades. Because the tool is simulation-driven and data-informed, it will remain relevant as mission profiles evolve and new materials and design features are introduced. Its flexibility integration makes it a natural fit within both current and future engineering workflows. The tool developed through this project is expected to have a functional lifetime of 10 to 30 years. This estimate reflects the typical service life of modern aircraft planforms, which often operate for several decades. As long as these aircraft remain in use, the need for accurate mission-specific structural assessments will continue. Moreover, the methods used in this tool, such as combining mechanical and environmental loading with simulation and data analysis, are not platform-specific. They are adaptable and can remain relevant even beyond current aircraft models. Beyond the direct application to aircraft loads, the tool's framework can also support future efforts in materials qualification, life extension programs, and airframe certification. The tool will primarily be staffed and operated by aerospace engineers who are directly involved in structural analysis and airframe development. These professionals need accurate load inputs to model fatigue, damage, progression, and durability. Simulation specialists will use the tool during testing phases and design iterations to evaluate how different mission profiles affect proposed structures, and in some cases, data analysis and software developers may also support tool operation by preparing inputs, maintaining compatibility, or adapting the tool for new requirements. Importantly, the tool is being designed for accessibility and usability by both government personnel and contractor teams. This ensures it can be applied across the full spectrum of the development pipeline, from early research to operational readiness. The client for this proposal is the Air Force Research Laboratory, which is seeking a way to generate realistic mechanical and environmental load spectra to improve the structural assessment of aircraft. Their goal is to replace generic or overly simplified loading assumptions with mission-specific validated data. The AFRL needs external help because this problem spans several complex domains: flight data analytics, structural simulation, materials science, and machine learning. These capabilities are well beyond the specialty of the AFRL. This is why they have outsourced it via this proposal. The primary goal of this project is to develop a load spectrum generation tool that produces realistic, mission-specific load profiles for aircraft structures. These profiles will not just be basic mechanical loads, but also dynamic behavior, aeroelastic interactions, and environmental factors. A key focus is the accuracy of these spectra by validating them against known historical data. This builds trust in the tool and its outputs, ensuring suitable use. Ultimately, the tool will support a range of engineering needs, from early-stage aircraft design and simulation to structural integrity assessments and fatigue life prediction. It will be built to align with AFRL's current analysis workflows and integrate easily with widely used platforms like ANSYS and Nastran. Current research reinforces the importance of tailoring load spectra to actual mission use to improve predictive accuracy. That is cited by ICAF 2023. This project is driven by several key research questions that both define the technical scope and the innovation we aim to deliver. First, we ask how to combine various sources of loading, mechanical, dynamic, aeroelastic, and environmental into one cohesive time-resolved load spectrum. This is essential to reflect the full range of stresses an aircraft faces during real missions. Structural fatigue under combined mechanical and environmental loading has long been recognized as a critical concern. That citation is from NASA, 1973. We also need to determine what fidelity is required for these spectra to be accurate. Too much detail is inefficient, and too much is missed failure risks. Another important question is how mission-specific variables like flight profiles or operational environments affect the loading patterns. Capturing this is vital to making the tool accurate and flexible. We also consider the limitations of real-world data. How can we construct realistic load histories when only partial or low-resolution sensor data is available? Then, we examine how different structural materials behave when subject to complex, multi-source load spectra over time. Next, validation is an important cornerstone. We must identify the best methods for comparing simulated spectra to experimental and historical data, ensuring credibility and usability. Finally, the tool must fit within existing engineering workflows. We must ask how to design the system so it complements current analysis tools. The methods for this project combine physics-based simulation, data science, and validation strategies. We begin data acquisition, sourcing flight data from test flights, operational mission logs, and publicly available environmental data from agencies like NASA and NOAA. This approach builds on prior studies that emphasize the importance of real-world load histories in structural evaluation. That citation is from NASA, 1967. Once the data is collected, we move on to load modeling. This includes using FEA and full vehicle kinematic simulations like those in MSC Adams. We will also apply proper orthogonal decomposition to reduce, otherwise known as POD, to reduce computational complexity. Neural networks will be trained to supplement physics. Environmental effects such as temperature, humidity, and chemical exposure are then time-aligned with the mechanical loads to capture the complete operating conditions. This alignment is critical for accuracy. This project leverages probabilistic and simulation-based approaches proven effective in modeling fatigue in composite materials. That citation is from Pineda and Benedict from 2010. For validation, we will compare our generated spectra to known historical load cases and results from physical fatigue testing. This ensures credibility and builds on AFRL's confidence in the tool. High-fidelity simulations have proven effective in predicting aeroelastic and gust responses for validation purposes. That citation is from Mitchell, Perron, and Saigat from 2019. Finally, the tool will be developed in MATLAB, Simulink, and Python with a focus on compatibility with Nastran and ANSYS. This will support smooth integration. The deliverables in this project were selected specifically to meet Air Force's research laboratory's needs for accurate mission-relevant structural data. The centerpiece in this load spectrum generator itself. The centerpiece is this load spectrum generator itself. It creates realistic time-resolved loading profiles that reflect the true conditions of an aircraft experiences during its missions. This is essential for structural design, fatigue analysis, and airframe certification. Each output is planform specific, meaning the spectra are not based on generic assumptions, making them flexible and directly applicable to AFRL's ongoing and future programs. To ensure credibility, we also will include a validation datasets and representative test cases. These will show that the tool produces reliable data when compared to historical and experimental data. This helps its credibility. The integration framework ensures the tool will be usable with systems the AFRL already relies on, like Nastran and ANSYS, without needing to change workflows. Finally, this project will include a comprehensive technical report that documents the models, methods, assumptions, validation steps, and recommendations for future use. This is the timetable for the project. For the first 2 months will be reserved for planning and defining requirements. Month 2 to 4 will focus on data collection and preparing. Sorry, that was from month 2 to 6.5. From month 6.5 to month 14 will be for spectrum generation. From month 14 to month 22 will be for simulation and validation. And the final half month will be for integration and reporting. Limitations and obstacles. While this project is technically feasible, there are several limitations. The first is data access. Generating realistic spectra requires detailed access to data, both environmental and flight specific. Some of this information may be classified or restricted, requiring clearances. Second, the tool requires on high-fidelity simulations such as FEA and aeroelastic modeling. These methods are extremely computationally intensive and may result in overflow errors or extreme computational time. Another challenge is the complexity of the modeling itself. Combining all these spectra across mission scenarios introduces significant technical overhead. It requires careful structuring and iterative model refinement to maintain accuracy and performance. Lastly, this is a cross-disciplinary project. Expertise is needed in several fields, like flight mechanics, structural analysis, environmental effects, and material science, plus machine learning. By recognizing these challenges early, we can plan mitigation strategies and ensure the successful delivery of a robust and reliable tool. Several critical resources are required for this project are already in place and accessible. First, we have access to the Cray computer cluster at the ERAU Daytona Beach campus. It is a powerful computer that allows high performance and accurate simulations. In terms of software, we have licenses for all FEA tools, CFD solvers, and dynamic modeling platforms like MSC Atoms that allow for complex mechanical and environmental load interactions. We also have CAD tools readily available and to support geometric modeling and integration. Because these resources are already secured, no additional costs is needed for these specific resources. New resources that are needed. While many tools are already in place, several will need to be acquired or bought. The most critical is the mission-specific flight data. This includes detailed sensor outputs, flight logs, and operational parameters unique to the aircraft. Access to this data will involve coordination with military units and will require personnel to obtain security clearances. Next, it will need validated materials data. This includes fatigue and degradation properties under complex loading conditions, mechanical, thermal, and chemical. Such data is essential. Additionally, we plan to use test coupons or small-scale physical models to validate the tool's outputs for accuracy. Finally, depending on the sensitivity of the data, we may need secure storage and data handling infrastructure to ensure compliance with government and DoD requirements. These resources are essential to ensuring the tool is accurate, validated, and aligned with AFRL's technical and security standards. The total personnel cost for this 2-year project is estimated to be $156,000, distributed across 4 roles. The project lead will guide the technical direction and ensure coordination. This role is budgeted at 30% full-time effort over the full 24 months, totaling $48,000. Their leadership is critical for aligning with client objectives and technical quality. The simulation engineer is responsible for developing the core modeling framework, integrating FEA, CFD, and environmental data. This role is allocated at 50% effort over 18 months, amounting to $53,000. A graduate research assistant will provide essential technical support, handling simulation setup, data processing, and routine model validation. This position is full-time over all 24 months, with a total stipend of $40,000. Their contribution will be critical for executing the day-to-day tasks efficiently. Lastly, we have budgeted to have a subject matter expert, or SME, who will contribute approximately 100 hours over the project's duration at a rate of $150 per hour. These results in $15,000 and provides access to high-level expertise. This team ensures the right balance of leadership, technical execution, and expert input while maintaining cost efficiency. The personnel that we are paying for in this structure includes the 4 key roles as stated before. Project lead is responsible for overall coordination, technical oversight, and assuring alignment. The structural engineer will carry out core technical development, building, and integration simulations. Integrating model simulations, Their focus is on structural aeroelastic environmental modeling and ensuring capability within existing tools. A research assistant will provide critical hands-on support throughout the project, assisting in data handling, simulation setup, running test cases, and post-processing results. Their full-time effort supports the technical team by managing routine but vital tasks. Finally, the subject matter expert will provide high-level technical input in specialized areas such as flight dynamics and complex structural loads. Their contributions are critical for accuracy. Each role is filled by personnel who are qualified to match their role. The project lead will hold a PhD or master's in aerospace engineering or material science with demonstrated experience in project leadership. Familiarity with DoD research protocols is preferred. The simulation engineer should at least have a bachelor's in aerospace engineering, though a master's is preferred. They must be proficient in FEA, computational fluid dynamics, and programming languages used in environments. The graduate research assistant will be a student enrolled in a master's or PhD program in aerospace or related field. They should have hands-on experience with CAD, simulation workflows, and basic data processing. The subject matter expert should bring over a decade of specialized industry or research experience in flight dynamics, structural loading, or related fields. A PhD or master's degree is required, along with strong applied background. At the conclusion of this project, we will deliver a set of tools and documentation that directly supports the client's operational and research needs. The core product is the load spectrum generator. We will also provide a validation data set to ensure the load spectrum generator is correct and increase reliability. To ensure the tool is usable in real-world workflows, we will include an integration framework to connect with Nastran, ANSYS, and MATLAB. Finally, the final technical report will document the entire process, modeling techniques, validation methods, limitations, and future conditions, providing AFRL with a complete reference for both immediate and long-term use. These matter because they fulfill AFRL's core requirement, the ability to generate realistic mission-specific load spectra that can be used in structural assessments and design workflows. By providing tailored load histories, the generator replaces the need for overly conservative assumptions or generic inputs. The validation dataset is critical for building confidence. The integration framework ensures that what we deliver is not just technically sound, but also easily usable. And the technical report ensures transparency and long-term value. Following the completion of this development phase, we've allocated a final 1-month support period to ensure smooth transition of the tool to AFRL. During this time, our team will be available to assist with testing, address integration issues, and refine the tool based on any last-minute feedback. We will also provide detailed documentation, including user guides, installation instructions, technical background, and example workflows. The handoff process will involve direct coordination with AFRL personnel or designated contractors to walk through the tool's features, setup, and application. Since the tool is built with flexibility and compatibility in mind, it is intended for long-term use across different aircraft platforms, research projects, and certification efforts. These are the references that were used to document the narration. They're in alphabetical order in APA 7th edition. These are the image sources for all of the images throughout the slides. Thank you.